Alright. Alrighty, so let's go ahead and do problem number 3. It says after the bumper cars hit, oh no, they fall into this pillow, and we wanted to talk about what the pillow's purpose is. A lot of you wrote that the pillow cushions the fall. I know that it cushions the fall, but you need to talk about why cushioning actually matters in terms of impulse and momentum. So specifically what we have is, we have that Ft equals mv final minus mv initial. Now here's the thing, whether you have concrete or a pillow, this is the same. This is the same for pillow or cement. And of course we don't want a kid falling on cement. So here's actually what happens. What happens is the pillow increases time and the force actually decreases. And what actually means here, what this actually means is the impulse is the same. And what happens is we reduce force by increasing the time. And that's the key. That's the key to doing this problem. So these are the graphs. I'm sorry they're drawn so badly, but this is what you were given, and you're expected to figure out what the position graph or the acceleration graph. You're supposed to fill in the appropriate graphs on this problem. So I'm going to go ahead and do that now. So for this first one, we're actually going to start off slow going backwards. We're going to start off fast going backwards, and then we're going to slow down, and then we're going to speed up going forward. So it should actually look like this. And since the slope of the velocity graph gives us the acceleration, we're just going to get a line like that. Now for this next one, we're actually going slow backwards, and then we speed up, and then we're going fast backwards, and we slow down. And so that means our acceleration, being the slope of the velocity graph, looks like this. So these are the graphs that you should have got on your final. Alright, now the kids go to this ride, and we want to see if it I guess it's broken down, and you know, I know I had a different weight for these kids, and this might be a good exercise, so here's what I'm going to do. I'm going to assume that these kids, they're going to have we're going to give them a combined mass. We're going to give them a combined weight of, we're going to make them 1,600 newtons. Okay, so this means a couple things. It means that since Fg is mg, and we've got 1,600 newtons, we're going to have their m times 10, and that's going to give me the mass of these two kids together is 160 kilograms. Well, the kids in the ride and all that stuff, so 160 kilograms. Now let's draw the free body diagram of what's going on here. We're going to have a normal, we're going to have the weight, and we're going to have a friction force going this way. Now let's go ahead and try to set up, because we've got some kind of pushing force here, but I'm not sure how big that's going to be. So let's just balance our forces in the y direction. That's Fn equals Fg, and that means Fn is going to be 1,600 newtons. Now we can use our friction formula. Friction is mu times Fn, and that's going to give us 0.4 times 1,600, and that's going to give us 480 newtons. And so, again, I'm using different numbers than what was perhaps on the exam, so this is actually good. It'll force you to kind of review the problem with the different numbers. And so now what we're saying is the pushing force is 400 newtons, but friction, the maximum friction possible is 480 newtons. So what that means is in this particular case, we're going to push with exactly the same force, we're going to push with 400 newtons, and that means friction's going to wipe it out at 400, so it doesn't move because the maximum friction is bigger. I've got to push with at least 480 to get it to move, because force push is less than friction max. All right.